Okay, so here we're going to do this limit. Notice when we plug in infinity, we get infinity raised to the 1 over infinity, and 1 over infinity is essentially 0. So this is the indeterminate form of infinity to the 0. So whenever you have these indeterminate forms of 1 to the infinity, 0 to 0, infinity to 0, whatever, the procedure is pretty much the same. Step 1, let y equal whatever your function is that you're taking the limit of. Step 2, take the natural log of both sides and use the properties of natural logs to simplify this right side. So this is the ln of y equals 1 over x times the natural log of x. Now we take the limit of both sides. So we take the limit of the natural log of y, in this case we're taking the limit as x goes to infinity, equals the limit as x goes to infinity of, well, let's multiply this through. We have the natural log of x over x. At this point you might need to manipulate this, because remember, at this point in our procedure this has to be either infinity over infinity or 0 over 0. But here when we multiply, when we go to infinity, the natural log of infinity is infinity. When x goes to infinity, that's infinity. Infinity over infinity, we can use L'Hopital's rule. So we get the limit as x goes to infinity of the natural log of y. And because it's infinity over infinity, L'Hopital's rule said this limit is going to equal the limit as x goes to infinity of the derivative of the natural log of x, which is 1 over x, divided by the derivative of x, which is 1, but 1 over x over 1 is just 1 over x. And that we can take the limit. The limit as x goes to infinity, we get 1 over infinity, which is 0. So the limit as x goes to infinity of the natural log of y is equal to 0. Now, just way back at the beginning of the course, remember the limit of a function is equal to, so the limit as x approaches some number, whatever, of a function, this is equal to the limit as, well, what we can do is we can take the limit of our function, it's basically f, and that's the limit as x goes to a of our function, which it's our function of x. Right? So this is, we can think of as the natural log of y as the limit as x goes to infinity. Now, this is a technical part. It really doesn't matter. I could do e raised to both sides here, but technically we want it in this form, e raised to the both sides. Why? Because e raised to the natural log of a is a. So e raised to the natural log of my limit is just the limit as x goes to infinity of y. E to the 0 is 1. But remember, what is y? Y is x to the 1 over x. So we found the limit as x goes to infinity of x to the 1 over x. I'm just substituting for y into this. We found that's equal to 1, and that's what we wanted to find. So that limit, in this case, is equal to 1. But all intermediate forms of infinity to 0 are not equal to 1. This one happened to be.